Good afternoon. Welcome, everybody. It's a great honor to have Dr. Fang here today giving the grand round lectures. Dr. Stan Fang is the Houston Merit Professor of Neurology and the Director Emeritus of the Center for Parkinson's Disease and Other Movement Disorders at the Columbia University in New York City. He served as the President of the American Academy of Neurology from 2001 to 2003. He served as the Scientific Director of Parkinson's Disease Foundation from 1979 till 2016, when the foundation merged into a new Parkinson Foundation. In 1985, he co-founded with Dr. David Maston the Movement Disorder Society and was elected as the first president. He was the founding co-editor of the Journal Movement Disorders and the associate editor to the Journal Neurology, each for more than 10 years. Dr. Fang has twice served as the chairman of the Advisory Committee on the Peripheral and the Central Nervous System Drugs for the FDA. And Dr. Fang co-founded the Parkinson's Study Group in 1986 and was co-chaired for 20 years. And he organized and executive the development of multiple scales clinically used for movement disorders, including the well-known UPDRS and others in tremor dystonia and chorea. He participated in numerous clinical trials, including the Levodopa trial to study the effect of levodopa therapy on the natural history of PD, and also the first controlled surgical trials for the fetal tissue transplantation for patients with advanced Parkinson's disease. He was the chairman and the chief of organizer of the World Parkinson Congress from 2006 to 2013. He received numerous awards from a number of neurological organizations, including AAN, ANA, and MDS. In 2002, Dr. Fang was elected as a member of the Institute of Medicine of the U.S. National Academies, now called the National Academy of Medicine. He has published more than 550 papers and 26 books and 276 book chapters, reviews, and commentaries. Dr. Fang has trained over 130 movement disorder fellows, including many who are professors of neurology around the globe. As a legendary figure in the history of Parkinson's disease and movement disorders, he also has walked through the history of discovery and the development of levodopa, the most powerful medication on the treatment of Parkinson's disease, which is a story he will talk about today, and as requested by the MDS, the president and the committee, will be kept into MDS archives. Without further ado, please welcome Dr. Fang.
Thank you, Dr. Z. It's nice to be at an institution where one of my fellows, former fellows, was now doing so well, and I thank him very much for the invitation. It's a pleasure to be back here. I was here a number of years ago. Before I start my talk, though, I want to dedicate this to Bud Rowland. Dr. Rowland was my mentor. He was a young attending when I was a resident, and then I worked in his lab as a third-year resident. He's supported me ever since. We became friends, colleagues, and he himself is a giant neurology, president of AAN, ANA, many other organizations, very friendly, editor of the Journal of Neurology, editor of books, Merritt's textbook of neurology, and so forth. And a real human being, friendly to everybody, supports everybody, and we're going to miss him. He died 1 week after he had a stroke, and it was just exactly 1 week ago that he died, so we remember him. What I want to talk about today is the Levodopa story. I think it's interesting for young people. We all know that levodopa is the most important drug in Parkinson's disease, and really a revolutionary treatment. But how did we get there? We almost didn't get it. We almost lost it. It's very appropriate to talk about Parkinson's this particular year because this is the 200th anniversary of James Parkinson's booklet, the essay on the shaking palsy. 200 years is a long time, it seems like, but we've gone a long way, and most of the advances have been in the last 50 years. And this is the story of Levodopa, because it's just 50 years ago that Levodopa was first used in high dosage form. where will we be without it, right? So it is the most effective drug that we have. And everybody agrees it's the gold standard for treating Parkinson's disease, at least the motor symptoms of Parkinson's disease. There was no precedent for levodopa. It's truly revolutionary. It didn't evolve from anything else. And yet, again, which I'm going to emphasize in my little story today, is that how it was almost lost. We almost didn't get it, and it was missed. It would have been missed. And the Movement Disorder Society's journal, Movement Disorders, had a big issue in January 2015, exactly on levodopa, not only its history, but its current status, all the other compounds that went with it, all the enzyme inhibitors that makes it more effective, and various forms of levodopa that are in the pipeline because of all the problems that levodopa also has. The three heroes I'm going to be talking about and you'll hear about is Arvid Carlson, Ole Ornikevich, and George Kachis, and I'll tell you exactly what their roles were. And we owe them a great debt, and they're really the heroes of this story. So what was it like treating Parkinson's before L-DOPA? We can go back to the 1950s, 1960s. I was a resident then. I started in 1959. The main treatment were anticholinergics. Artane, Cogentin, they're still around today. These are just two of them. There were many other anticholinergics that are probably still around too. But they were useful. I remember people, Louis Daucher was the head of our Parkinson clinic at Columbia when I was a resident. And he would bring people in for a week of physical therapy. Physical therapy was very important then, still important today, but more important even then because we had so few other treatments. And if they kept getting worse in the clinic, and we tried one drug, anticholinergic, we tried another anticholinergic, and so forth, eventually brings them in for physical therapy. They get better a little bit, they go back, and within a few weeks they're back to where they were again. It was a pathetic way of dealing with people with Parkinson's disease. We have very big problems in helping them cope with the quality of life. And all the residents at the Neurological Institute in those days had to have a month's rotation in the Parkinson clinic with Lou Daucher. So you got to see these patients, and no one really wanted to go there because there was not much you could do. And that was what it was like. There was also stereotactic surgery. In the 1950s, Irving Cooper popularized cryothalamotomy. There were other kinds of approaches earlier, but the stereotactic surgery was helpful. People did lose their tremor. They had a little bit better mobility for their akinesia. And it was very popular. Irving Cooper, I went to his office once, and he had on all four walls of his office filled with plaques of honorary memberships of one neurological surgical society or neurological society in many countries in the world. And he was very well esteemed for his role in stereotactic surgery. Here's a picture of Irving Cooper, and this was a title cover of Life magazine in 1959. It was a story about Margaret Burke White, a very famous aviator and journalist who had Parkinson's, and Irving Cooper operated on her. That's not Burke White in the picture. This is some model, I guess. This is her talking to Irving Cooper and one of Irving Cooper's assistants. And so this was the popular treatment in that day. So then how do we get to L-DOPA? Well, to start the story, we have to really go back to dopamine. Dopamine was chemically synthesized in 1910, two separate institutions, one in England, the Wellcome Labs by Barger and Ewens, and the other one in Monack and Jakobson at the Pharmaceutical Institute in Berlin. This was 1910, they synthesized it, both independently did this, and in the same year, Barger teamed up with Henry Dale, later Sir Henry Dale, to try to see what does dopamine do, and they discovered it has a sympathomimetic, epinephrine-like effect. It was Henry Dale who, years later, 1952, suggested the name be called dopamine. Prior to that, it used its either full chemical name, 3,4-dihydroxyphenylethylamine, or more commonly used as 3-hydroxytyramine. Those are the names of the drug. But Dale recommended in 1952 why it should be called dopamine, because by then it was more closely allied with dopa rather than with tyramine. And they said, well, it's not related to tyramine at all, it relates to dopa, let's call it dopamine. And that name stuck and been used ever since. The following year, in 1911, Casimir Funk, also in London, at the Lister Institute, synthesized D-L-Dopa. Casimir Funk, before I get to that, this is the chemical structures of dopa and dopamine, as you can see here, and you're all familiar with that. So who was Casimir Funk? Well, he was Polish, first of all. He was born in Poland anyway, but he was mostly educated in Germany. He studied in Berlin, and later he emigrated to London, and that's where he synthesized D-L-Dopa. He wanted to work on the pharmacology of D-L-Dopa, but at that time the Lister Institute was particularly interested in beriberi and other vitamin deficiency, and they wanted to know what was the cause of beriberi, so he was assigned that work. He discovered it was niacin deficiency. Later on, it was Funk who actually coined the term vitamin. In the middle of World War I, in 1915, he moved to the United States. He continued to work on vitamins. He made many other discoveries while in the United States. He discovered thiamine, riboflavin, ascorbate, and vitamin D. And after his death, the Polish Institute of Arts and Sciences of America annually honor a Polish-American scientist with the Casimir Funk Natural Sciences Award. So he's well known among scientists, and particularly those who Polish extract. When we move on to 1913, this is when Marcus Guggenheim, working with at Hoffmann La Roche in Basel, actually isolated L-Dopa, Levodopa, the natural substance from legumes, Vicia faba, the faba bean plant. Although levodopa is an amino acid, it's not taken in your diet. It's not like other amino acids that we eat and ingest. It has to be synthesized in the body. And so very few plants actually make levodopa, and faba bean is one. And even today, there's some poor countries that people will grow faba beans in order to eat that and get the extract from it of L-Dopa to try to help their Parkinson's. But you don't never get enough compared to what you can get in a single tablet of carbidopa levodopa. Anyway, Guggenheim isolated levodopa. He did self-testing on it. He ingested 2.5 grams. He immediately developed nausea and vomiting. He saw his urine turn black when it was standing in alkali. And it was Guggenheim who actually coined the term biogenic amines years later. So we can move ahead to the 1930s. By this time, there was a lot of interest in epinephrine, from the adrenal gland, what it was doing. And people began to consider, could L-Dopa and dopamine be possible precursors? But there was nothing much done about it in the early 1930s. It was later at that decade, though, that the link was found. In 1937, Hermann Blaschko, then at Cambridge, a refugee from Germany, he left, fortunately, in time about to escape Hitler and the Nazis. He went to Cambridge. He discovered the enzyme monoamine oxidase. He thought at that time monoamine oxidase was the enzyme that terminates the activity of the monoamine, the catecholamines anyway, most of the monoamines. But it actually is not true. It's inactivated by reuptake. But that was the thought at the time. In the following year, in Germany, Peter Holz discovered the enzyme dopa decarboxylase, and he showed that it can convert tyrosine to dopa. Dopa to dopamine. Whereas tyrosine to dopa was still not known how dopa got formed. But at that time, they had the enzyme degrading dopamine and an enzyme synthesizing dopamine. So by the end of the 1930s. And this is the pathway, as you can see here. We have dopa going with the dopa decarboxylase to dopamine. And here's MAO. COMT was discovered, catechol methyltransferase was discovered by Julius Axelrod. It was also the degrading pathway here. And here, of course, is the way to norepinephrine. But this part was how dopa was formed was still unknown. By 1939, Peter Holz showed that proposed that the mechanism of how do you get the dopamine and norepinephrine and epinephrine goes through dopa and dopamine. And Blaschko, in a separate independent paper on his own, proposed the same pathway. So this pathway was now proposed by the end of that decade. In the middle of the war, Peter Holst, still in Germany, found that dopamine could lower blood pressure in some animal species. And by 1946, at the end of the war, von Euler discovered that norepinephrine was the neurotransmitter at the sympathetic nerve endings. Later on, in 1970, von Euler shared the Nobel Prize with Bernard Katz, who discovered that acetylcholine was the transmitter at the peripheral nerve, motor nerves. And Julius Axelrod, as I mentioned his name before, got his Nobel Prize because of the mechanism of release and reuptake of the catecholamines from nerve terminals. In the 1950s, people were interested now in dopamine. They found some dopamine in small amounts in many tissues of the body. And by 1952, Peter Holst discovered that pyridoxal phosphate was the cofactor for dopa decarboxylase. What we now have is that Blaschko had now moved to Oxford from Cambridge. He showed that in the adrenal gland, epinephrine was bound in granules, and this led to the way that the future realization that the monoamines are found in granules and nerve terminals. So this was first found in the adrenal gland that way. We bring Ole Hornikewicz into the picture now, because Ole Hornikewicz trained in medicine in Vienna, but he got a fellowship to study under Blaschko in Oxford. And Blaschko gave him the task of looking, what does dopamine do to blood pressure? And he showed that it did change blood pressure a little bit. He also tested L-Dopa, found the same effect. And that publication, as you can see here, in 1958. So Ole Hornikewicz was now involved with dopamine in this first way. Now, who was Hornikewicz? And he's still alive. He was born in 1926 in Sickev. It was Poland that day. Between the World War I and II, that area was Poland. After World War II, it's now Ukraine. So it was Eastern Poland, now Western Ukraine. It's in the outskirts of the big city Lvov in Western Ukraine, formerly also in Poland. Now, he was the youngest of three boys in a fourth-generation family of Catholic priests. Now you can ask, well, how can you have Catholic priests and have children? Well, it turns out, and I had to learn about this, is that in Eastern Europe, Russia and Ukraine, Russia mainly, the Eastern Orthodox Church, the priests can marry and have children. West of that, especially in Poland and further west, the Catholic priests could not marry and not allowed to have children, therefore. But in Ukraine, there was a big battle between Catholic priests converting to Orthodox in order they can marry and have children. So the Catholic Church made an exception for those priests in that part of the world in order to keep them as Catholics, to allow them to marry and have children. So that's how Catholic priests were able to have children in Ukraine and Eastern Poland. Of course, in August 1939, as you know from history, the pact between Germany and Russia, Soviet Union basically divided Poland up, and the eastern part of Poland became Soviet Union. Hornikewicz's mother had relatives in Vienna, so they were able to move to Austria and Vienna because of that. And he essentially grew up in the war in Vienna. He studied at the University of Vienna, got his MD, but he immediately went into pharmacology. He did not practice medicine. He got a position at the university in the Pharmacological Institute, and by 1956 he got a scholarship to study and work with Blaschko on the monoamines, and that's how he got to England and the dopamine. And here's a picture of Herman Blaschko visiting Hornikewicz's lab in 1982 when Hornikewicz got a new lab at the University of Vienna, and had a big party and invited Blaschko to come. Well, we still didn't know how we got L-Dopa. And there was a lot of labs trying to work on this and trying to figure this out. We all knew about tyrosinase. Tyrosinase converts tyrosine to dopa, the dopamine in skin pigment, eye pigment, hair pigment. But that's not the way it works in making dopamine in the central nervous system or peripheral nervous system. So the mystery was on how to work, and the labs are on. And the race was won by Sidney Uniform's lab at NIH. Toshiharu Nagatsu was a postdoc, and he was assigned this task to try to find this enzyme that would convert tyrosine to dopa, and he did, called tyrosine hydroxylase, and published in this paper in 1964. Interesting story is that Nagatsu, when he finished his training, his postdoc fellowship, he went back to Japan, had his own lab, and began working in tyrosine hydroxylase, and he looked at the cofactor for tyrosine hydroxylase was GTP cyclohydrolase 1. He was working on this at the time when at Columbia, Toby Nygaard and Kirk Williamson were looking at families with dopa-responsive dystonia, and they mapped the gene to 14q. But they didn't identify the gene, they just knew the map. But Nagatsu immediately recognized this is the area of where GTP cyclohydrolase 1 is located. He had been working on that. He teamed up with Sagawa, who first reported dopa-responsive dystonia, and looked at his families, and they found the actual gene. It was this gene. And so that, again, you start with one thing and you end up with something else, and we found the gene for this particular form of dystonia. And this is the pathway, and you can see it up here. Number 1, this is the GTP cyclohydrolase 1 gene, and this is the pathway to form tetrahydrobiopterin, which is the cofactor for tyrosine hydroxylase, also for phenylalanine hydroxylase and 5-hydroxytryptophan hydroxylase. All use the same cofactor. And here we have it here in this picture. So let's turn our attention now. How did dopamine get associated with Parkinson's disease? And this story probably starts again at Bernard Brody's lab, at NIH and Bernard Brody's lab this time. But actually, we can go back even further to reserpine. The Rauwolfia serpentina plant in India, pharmacologists there have been working with this grounded up the plant material and gave it to people. And they showed it had a calming effect. It also lowered blood pressure. And up to that time, there was no treatment for hypertension. When I went to medical school, it turned out to be reserpine was the only treatment. So there was a lot of interest in the Rauwolfia plant. And the SIBA pharmacologists at Basel got the plant and isolated reserpine and marketed reserpine. Reserpine became the first drug for this. But because of the it's also, quote, sedating effect, which we now would call drug-induced Parkinsonism. It was called neuroleptic. And it was this neuroleptic property that Bernard Brody was interested in, and he decided to work on it. And by 1955, showed that reserpine releases and depletes serotonin in the brain. They published this paper. Pletcher was a postdoc from Switzerland who went back to Switzerland afterwards. He became the head pharmacologist biochemist at Hoffman LaRoche Laboratories and responsible for the development of many drugs, antipsychotics and benzodiazepines there. But it was in this lab also that certainly just prior to the discovery of reserpine's effect, that Julius Axelrod was made chief lab tech. I mentioned Alfred Pletcher's name. He came as a postdoc. Arvid Carlson came as a postdoc in 1955. So he was there at the time of this exciting discovery. And so Bernard Brody, most people probably here don't know him, he was considered the father of modern biochemical pharmacology. He was actually born in Great Britain in 1907, but died in the United States in 1989. His family moved to Canada when he was still a youth, and he was educated in McGill, But he went to NYU in New York to get his PhD in biochemistry, and after he got his PhD, he was given a lab doing biochemistry at the Goldwater Memorial Hospital, which was affiliated with NYU. Brody's early work, he showed that humans and lab animals did not differ too significantly in responding to medications, and he published also at that time a basis for how to treat malaria. So he was a well-known biochemical pharmacologist at that time. In 1946, he hires Julius Axelrod as one of his lab techs, and together they did many great works. They showed that certain non-aspirin analgesics that caused hemoglobinuria was due to acetylcholine, and that a metabolite of this, acetaminophen, was also an analgesic that was safe, and this led to the development of Tylenol as an analgesic, but that was safe to take. Brody was recruited to NIH to run a lab at the National Heart Institute of chemical pharmacology, and he brought Julius Axelrod with him. And he was studying the effects of serotonin and norepinephrine in the heart and brain when this sedative effect, this neuroleptic effect of reserpine came into his awareness, and he began to study it. Brody went on, he won the Lasker Award in 1967, the National Medal of Science in 1968. And here's a picture of Bernard Brody, and here's a picture of Julius Axelrod. Now, Axelrod was born in New York City, and he died in 2004 in Washington. He went to City College of New York, graduated in 1933. He wanted to be a physician, but he could not get accepted to any of the medical schools in New York. He applied to them all, he was rejected. So after he got his degree at City College, he became a lab tech at NYU. He worked in the Department of Health. He was testing vitamin supplements that were added to food for the city of New York. And he would go to night school and got a master's degree at NYU in 1941. By 1946, he gets this job with Bernard Brody. I already mentioned some of the early work there at the Goldwater Memorial Hospital. And when he went to NIH, and Brody got interested in the catecholamines and serotonin also, Axelrod on his own was beginning to work in his lab, and he worked out the mechanism of the sympathetic nervous system pathways. He also worked on caffeine, codeine, and other things. But Axelrod couldn't really advance anymore until he had a PhD, so he took a leave of absence in 1954 from Brody's lab, went to George Washington University, got his PhD in 1 year. They accepted a lot of his research papers, and NIH hired him back as a section chief. It was probably all rearranged in advance. Once he got his PhD, he had his own section because he was recognized as a brilliant scientist at that time. As I mentioned earlier, he discovered COMT as well as the mechanisms of release of the monoamines and shared that Nobel Prize in 1970. So I mentioned also that Arvid Carlson went to Brody's lab. So he comes at the time they were working on reserpine and showing that it released serotonin in the brain. He only spent 6 months in the lab, but he suggested to Brody, why don't you start working on what reserpine does to other monoamines as well. Brody wasn't interested. Brody thought that was it. We know the answer is serotonin, diminution of serotonin in the brain, that's what causes it. Carlson was assigned a project by Brody to work on what does reserpine do to platelets, and he showed that reserpine does deplete serotonin in platelets. And by then, his fellowship was finished. He goes back to Lund, Sweden, and has his own lab. So Carlson, who's still alive, and he was born in 1923 in Uppsala, Sweden. His father was a historian and obtained a faculty position at Lund University, so Arvid grew up in Lund. In World War II, he had to serve in the Swedish military because, like many countries, Switzerland included, tried to stay neutral in the war, and Sweden was neutral in the war. They had to have their own standing army to keep their borders safe from attack. And after the war, he got his MD degree at Lund University. Again, he did not practice medicine like Hornikevich. He went right to the pharmacology lab. He joined the faculty at Lund, but his work was on calcium and vitamin D. But he became interested in biochemical pharmacology, and some of the senior pharmacologists at Lund University suggested, why don't you go to Brody's lab and get some training in this field. So that's what he went to, that's why he got a fellowship. He went to Brody's lab for 6 months, and I told you he worked on the serotonin and platelets. At the time, Brody was working on the serotonin and brain. But when Carlson came back to Sweden, he decided to follow up his own suggestion to Brody, why don't we see what reserpine does to other monoamines besides serotonin. So by the time he gets back, though, dopamine was already, somebody already found that reserpine released norepinephrine in the CNS. That was done in Edinburgh. But fortunately for Carlson, he teamed up with a very innovative histochemist, Hillarp, in Lund. Hillarp was responsible for developing the fluorohistochemical technique, which can map out the monoamine neurons in the brain, and his students all did that. And they showed, you can show how dopamine neurons arise from the nigra and so forth and goes up, and the serotonin comes from lower down in the brainstem and goes up and so forth. He teams up with Hillarp, and Hillarp was interested in the adrenal gland still, and so they showed that reserpine releases adrenaline from the adrenal medulla. And that's how his first project when he went back to Lund. But he goes back and he develops a new, very sensitive fluorescence technique to measure tiny amounts of dopamine in tissue. And he discovers, follows up the discovery of dopamine in the brain. His students started mapping out the distribution of dopamine in the brain, showing it was high in the basal ganglia. And Carlson was also interested in this neuroleptic effect. What is that? And so he does this famous experiment. It's a single page in Nature, when it was published in 1957. He takes rabbits, he injects them with reserpine, and they're all flaked out. They can't move, their ears are floppy. They have the neuroleptic effect from reserpine. Then he injects 5-HTP, the precursor of serotonin, along with a peripheral decarboxylase inhibitor, so it would get in the brain, and nothing happens. And then he takes the same rabbits, this time he injects Levodopa, and bingo. The animals perked up, he got this awakening effect, and I love this picture because the rabbits' ears are really erected straight up, and they're all alert, ready to go. Carlson submits this picture with his scientific paper to Nature. Nature accepts the paper right away, but rejects the picture. And the reviewer comment was, well, you don't need the picture because the paper says it all. The text says everything. So this picture didn't get published until Carlson's Nobel Prize-winning lecture gets published, and he presents this picture, and he gave us the permission to use this picture in the cover of that Movement Disorders Journal that I mentioned. So Carlson's still alive and doing well. By 1957, dopamine was found in the brain. Carlson's new technique supported that, and he also showed that if you gave reserpine to animals, dopamine gets depleted in the brain. If you give L-Dopa to those reserpinized animals, dopamine gets restored in the brain. These are the students who worked at Bertler and Rosengren who showed the distribution of dog's brain. At the same time, a neurologist in Japan, Isamu Sano, was mapping out the dopamine in a single patient, human brain, a single person with his brain, and showed again the high concentration of the basal ganglia. By the end of 1958, Carlson presents a summary of his work on dopamine in the brain at the International Catecholamine Symposium in Vienna. It gets published in 1959, and he postulates in that talk that maybe dopamine seems to be somehow involved with Parkinson's disease. And here's the title page of his review in Pharmacological Reviews about dopamine in the brain. Well, by this time, Hornikevich finishes his fellowship with Blaschko. And he became aware, when he goes back to Vienna, gets a lab at the Pharmacology Institute, University of Vienna. He was interested in the work that Carlson had just shown of the reserpine effect and the restoration of dopa. And he was impressed about his ideas that maybe dopamine is related to Parkinson's disease. But he wondered why didn't Carlson go ahead and measure dopamine in people with Parkinson's brain. So Hornikavich decides to tackle that project. He gets brains in Austria. It's possible for any doctor, when a patient dies, to get an autopsy without having to get permission. All you have to do is write down that you want the brain, and the brain is available. So they had a lot of brains of Parkinson's disease and post-encephalitic Parkinson's. And with his lab technician, Ehringer, they published in the December issue at the end of the year in 1960, in Clinical Grocery Strip, in German, the distribution of noradrenaline and dopamine in the human brain and the behavior and disease of the explorational system. And a few years later, he goes on and shows that there's also deficiency in substantia nigra in Parkinson's disease as well. This is Ehringer and Hornikavich's paper translated into English in the Parkinson Reviewed Parkinson and Related Disorders Journal. Ehringer, as I said, was his lab tech. And the policy of the lab, the pharmacology department in the University of Vienna, was that all papers had to be published in alphabetical order. And I would just mention that the name in the department with the lowest letter in the alphabet is the chairman of the department. Anyway, so it was Ehringer and Hornikavich's paper, and by 1966, 6 years later, he published his review in Pharmacological Review, showing a good correlation between striatal deficiency of dopamine with the motor symptoms of Parkinson's disease. It correlated very nicely. So he showed that most of Parkinson's motor symptoms, at least in these early stages, what we call bradykinesia and rigidity and so forth, relates to dopamine deficiency in the striatum. So now, how do we connect dopamine deficiency in the striatum that's related to Parkinson's symptoms, but pathology is in the substantia nigra? And this association has to do with the fluorescent histochemical technique of Hillard. And these are some of his students. In 1964, Dahlstrom, Fuchs, and they were mapping out the brainstem monoamine pathways that led to the basal ganglia. These were the serotonin pathways, the norepinephrine pathway, and the dopamine pathways, and showing that's where it comes from. And I remember there was big debate in those days. Malcolm Carpenter was a neuroanatomist at Columbia, and he didn't believe it. No one could find a link, an anatomical pathway that connected the nigra to the striatum, so he had doubts. But this fluorescence chemical technique showed it, so it became accepted. And then in Canada, in Montreal, Louis Poirier, the neuroanatomist at the French-speaking University of Montreal, and Ted Sorks, the biochemist at the English-speaking University of McGill in Montreal, teamed up. Poirier would operate on non-human primates, make lesions in the nigra, give the tissues to Sorks, and Sorks measured dopamine in the striatum and showed, again, a nice correlation. The bigger the lesion, the more the loss of dopamine. So again, we have the lesion now, as well as the anatomical pathways by fluorescence histochemistry, linking the nigra and the striatum with the dopamine. And of course, we get this picture in this pathway that you're all familiar with now. So let's turn now to levodopa's use in humans. The first use, as I mentioned earlier, was in 1913 when L-dopa was extracted from the Vishwafaba plant. But then the next one was during the war years, World War II years, in Mount Sinai in New York. Oster Zirkin injected 50 milligrams of dopa IV, saw a transient rise of blood pressure. And during the same year in Germany, Holtz and Kreeder injected 50 milligrams into their lab assistant and got a rise in pulse. I guess in Germany, you have to do what your boss tells you, right? Why is it going forward? There we go. But the interest then came, what about in disease states? And again, going back to Carlson's work in rabbits, reserpinized rabbits. Well, they were reserpinized humans. People who had psychiatric disease were being treated with reserpine, got drug-induced, what we call drug-induced Parkinsonism today. And the psychiatrists in Frankfurt, Zegvix and his colleagues, decided they should try L-dopa in these people and see if we can reverse, quote, the sedation effect. And they got some L-dopa from Boehringer and Sons laboratories and prepared who got the dope, and then they purified it in the sense that they are able to dissolve it in boiled water and inject different doses. They injected small doses at the beginning and slowly increased the dose. By the time they reached injection of 270 milligrams, patients started feeling ill, and by 350 milligrams doses, all patients were vomiting. They did find a transient reduction of the sedation effect. They said that more patients were a little more talkative, a little more animated. They tested many other things. They tested the effect of L-Dopa in the presence of monoamine oxidase inhibitors, the effect of pyridoxine, and so forth. And so they showed there was some additional benefit if you gave the MAO inhibitor with it. And that paper was published in 1960, the same year, and this was in February, the same year that Ehringer and Hornikiewicz published, which was in December. So they didn't know about what work that Hornikiewicz was doing. This was published directly based on Carlson's work. In the same year, at an international, well, I don't know, international, Japanese symposium, Sano, who had mapped out dopamine levels in the human brain, now also tested D-L-Dopa. Again, he was familiar with Carlson's work. 200 milligrams of D-L-Dopa IV, and he showed for a few minutes there was some improvement of progeria tremor, but, quote, no better than trihexyphenidyl. And that was in the symposium. The full paper was never published, just the abstract. In that same abstract, he reported measuring dopamine in the brain of one patient with Parkinson's disease. It was low in both the substantia nigra and the putamen. This was February. Remember, Hornikiewicz was working on it in December. So this was done in Japan, and there was no follow-up to Sano's work, however. Well, McGeer, smart pharmacologist at University of British Columbia in Vancouver, was interested in catecholamines, and he was, of course, got familiar with, again, with Carlson's work, and he decided to try D-L-Dopa also. So he prepared it in either capsules or in a suspension of methyl cellulose and gave different doses to patients with drug-induced Parkinsonism. It turned out that only 3 of those patients had drug-induced Parkinson from reserpine, the others from phenothiazines. And he also gave these patients diphenhydramine, Benadryl, which was one of the standard treatments for Parkinson's disease. It has anticholinergic effect. And he gave it, and he showed that there was only mild improvement with L-Dopa, and it was only in the reserpine group. The phenothiazine group did not get better. And even with the reserpine group, diphenhydramine seemed to be superior. Now, I'll call your attention to, he did report in his paper that he gave all the patients pyridoxine in advance of giving them D-L-Dopa. He was so smart, he knew that this was important to convert dopa to dopamine. But the problem is it might have been too smart because it converted dopa to dopamine in the peripheral circulation, and a lot of it probably didn't get in the brain, as we know that from subsequent studies in clinical trials. And so he lost it. He did not find the effect. This paper was published in JAMA in September 1961. He does mention Carlson, the Sano, Dekvit studies, but Hornikiewicz's paper didn't come out until December, and by then I guess his paper was accepted or whatever. Anyway, he didn't see it. He didn't know about Carlson, Hornikiewicz's paper, dopamine deficiency. So all this was done based on the reserpine work. And this was his title page in JAMA. Well, immediately after Hornikiewicz found the deficiency of dopamine in the brain, he decided to try L-Dopa in patients, the natural thing to do. He was, again, although he's an MD, he's not licensed to practice medicine. He teams up with Berkmeyer, a geriatrician in Vienna, who treated a lot of Parkinson patients. Berkmeyer was particularly interested in serotonin. He wanted Hornikiewicz to inject 5-hydroxytryptophan to the patients, but Hornikiewicz had none of that. He said, well, we have to do L-Dopa. The only L-Dopa that Hornikiewicz had, though, he brought back from Cambridge when he worked with Blaschko. So he had still a supply of some L-Dopa, and he gave up to 150 milligrams IV, and they reported a transient benefit of akinesia. They prepared the L-dopa the way Deckwitz did, and this paper was published in 1961. Subsequently, Berkmeyer and Hornikewicz injected many more patients and used again MAO inhibitors and other things, and they were finding the same thing. Small doses gave slight transient benefits. Higher doses caused nausea and vomiting. They had to purify it. They had to sterilize it, in other words, and it was a nuisance. It had to be injected IV, and they didn't know how to get enough benefit, but they stuck to their gun. They said it does help the patients, but others had trouble finding the same results. So here, anyway, this is the paper, again, translated into English that was originally published in German, the Berkmeyer-Hornikewicz paper on Parkinson-related disorders. And here he is, Hornikewicz and Berkmeyer together. Anyway, again, with the Hornikewicz work now published, others began to become interested in D-L-dopa. Andre Barbeau in Montreal started using oral doses up to 200 milligrams. He reported some benefit. Many others gave small doses as well, some IV, some oral. The list is here. From different countries of the world. Friedhoff was in New York. These authors reported some benefit, mild benefit. On the other hand, many other people tried it and failed to find benefit. And Mel Greer was at the University of Florida at the time, teamed up with a colleague and gave up to 1 gram of D-L-dopa to 2 patients and nothing happened. Others, Rinaldi in Italy, gave it with MIOI, failing, gave it with a double blind, so did Rene in Finland. And these all failed to find any benefit. And different doses, some were IV, some were oral. And so there was a lot of skepticism of whether dopa does anything specifically. Well, again, McGeer, very smart, decided he's going to try high doses of D-L-dopa. He teamed up with a neurologist. McGeer was a PhD pharmacologist. So he teams up with Zeldowitz in Vancouver with her patient. Then they gave up to 5 grams per day of D-L-dopa, building it up slowly, but only for several days. One patient took it longer, for 3 years. Only 2 showed some benefit. So again, at the end, they said it wasn't really worth it. It wasn't enough benefit over trihexyphenidyl. And this is the paper published in the Canadian Medical Association Journal of that work. So, again, McGeer concluded dopa has little to offer as a therapeutic agent in the treatment of Parkinson's. And a big review paper published by Roger Dubozan in 1965 said there was no evidence that the dopa effect is in any way specific or that it differs from the effect of other sympathomimetic amines. There was an international symposium at Columbia in 1965. I think it took place in November. I joined the faculty after leaving NIH, doing my research fellowship there. And I came in September. This was organized to take place in November, and I went to that symposium on pharmacology and biochemistry of the basal ganglia. It was, I think, a 3-day symposium. Many people were there. Carlson was there giving his talk, and Hornikewicz talked. And it was Hornikewicz's talk about dopamine depletion in Parkinson's disease that I became aware of it. That was 1965. And I immediately decided to change my field of work. I was working on sodium potassium ATPase of the electric eel, the sodium pump, and decided to work on the basal ganglia biochemistry, and I did that ever since, after I finished my work on the electric organ. Anyway, in that symposium, Hornikewicz felt that treatment with L-dopa was not practical, even though it seems to work, but it's not a practical treatment. And that was where it was in 1965. And here's the title page of the published book, published by Raven Press, the second book they ever published, Biochemistry and Pharmacology of the Basal Ganglia. And I think the only symposium related to that topic to this day. So by the mid-1960s then, neurologists, neuroscientists were very pessimistic that L-dopa had much to offer in the treatment of Parkinson's disease. And we could have lost it then. But then came along George Katsias. Now, George was born in Greece. Actually, he was born in Crete. His family comes from Athens, Greece. And his father was involved in politics. He was a newspaper reporter, or a publisher, I think. But he got in hot water with the politicians there, and he had to escape to Crete, and that's where George was born. But then they moved back to Athens. He grew up and trained in Athens. His father, as I said, was very involved in politics. He eventually became mayor before the war in 1934, and then after the war he became mayor again in 1951. George Kochis went to medical school in Athens, but by 1941, when the German army invaded Greece, his family wisely got out. They came to the United States, to New York, to escape the Germans. He all the way has an MD degree from Greece. It wasn't accepted in the United States. He would be required to go back to medical school. He applied to many schools, was rejected, but Harvard accepted him. He was interviewed by Harvard by a refugee from Nazi Germany who was sympathetic, and he took George on as a third-year medical student. He didn't have to repeat the basic science years, just the clinical years. So he got his second MD degree from Harvard, became a resident. First he interned in pathology and in medicine, then became a neurology resident in Mass General. But he was interested in research particularly, and in Mass General, there was a pharmacologist, Donald Van Slyke, and he worked in Donald Van Slyke's lab. But Donald Van Slyke was then going to be given a lab at the Rockefeller Institute in New York. It was Vincent Dole's lab. Dole was picked to be the head of this new federal government laboratory in Brookhaven, New York, Long Island, New York, and Stony Brook, Brookhaven National Lab. And so Dole was going to vacate that lab, and Donald Slyke was going to come. Meantime, Kochis and another colleague from Mass General came to Rockefeller Institute, and they worked under Vincent Van Dole for a few months before Dole left for Brookhaven. They worked with Van Slyke for a few years. Then he went to Brookhaven because Vincent Dole recognized he was very talented and he needed to staff his lab, so he brought Kochis to Brookhaven. So Brookhaven was the place where Kochis did his work. He began to get involved with manganese. He wanted to start in the middle of the alphabet of an element, and he started working with manganese. He measured its distribution, its absorption, elimination, kinetics. He worked on manganese miners. They showed that they had dystonia and Parkinsonism. And so he became involved with this, and he began becoming interested in neuromelanin. He felt that manganese interacts with neuromelanin, and so the phenothiazines, and he thought that somehow or other Parkinson's was related to the neuromelanin, the problem with neuromelanin, the deficiency of neuromelanin. Kochis was aware of the Carlson work and the Hornikevich work, but he really thought that was the wrong hypothesis. His hypothesis was the deficiency of neuromelanin in the niger was the cause of the symptoms of Parkinson's disease. So he began to try to build up neuromelanin in the brain. And the first thing he did was try melanin-stimulating hormone. But it turned out that it made the symptoms of Parkinson's worse. So then he went to DL-phenylalanine, of course, the precursor of tyrosine, the precursor of dopa, and so forth. But that also made the symptoms worse or had no effect. And you can see why it might make the symptoms worse. It might compete with tyrosine getting into the brain. And so tyrosine can't make, if it's not there, it can't make dopa and dopamine. And the third thing he tried was DL-dopa. Now, he had the advantage of being in a national laboratory, had a hospital. He was in charge of the clinical pharmacology there. He can bring patients in. There was no IRBs. There's no limit on how much time you can spend in the hospital. The government paid for everything. And he brought them in, and he convinced them to try DL-dopa. He tried all these other ones first, and build the doses up slowly. He wanted to avoid the nausea and vomiting. You can't get enough dopa in without nausea and vomiting, and that was the big problem. So he developed this way of doing it, tiny doses, baby doses, building up very little by little until he got bigger doses. And by the time he hit big enough doses, he had this revolutionary treatment on his hands. People got out of the wheelchairs and started walking. And so his paper was published in New England Journal in 1967, D-L-Dopa, and they went up to 16 grams per day. 16 patients were tested. He avoided the GI side effects, as I said. He has found marked improvement in 8 patients, moderate in 2. Of the 8 patients who received 12 grams or more, 7 showed marked benefit. But they did get the side effect of granulocytopenia in 4 patients. They did bone marrow examinations. They found vacuoles in the myeloid cells in 4 of 12 patients who had their exams. So he knew that was a problem. But he also thought that maybe it was the D-Dopa that did it, and we should just switch to L-Dopa, the natural substance. So he started immediately working on L-Dopa. Now, this is his paper in the New England Journal. Now, before that, or by the time that paper came out, Kotches presented his results of his work at the International Symposium that was organized in Montreal at the time of the Expo, the International the World's Fair, 1967, the Expo. And it was a big symposium. It wasn't only about basal ganglia, but it was a lot of basal ganglia and the catecholamines. I went to that symposium with my colleague Lucien Cote. We had done this work on the biochemistry of basal ganglia. We showed by that time that the substantia nigra was a hotbed of high activity of GABA and its enzymes, GAD, high activity tyrosine hydroxylase. We said it was a powerhouse of metabolic activity in the nigra, even though it was thought to be a dead organ. And it was in that symposium, after we gave our paper, that David Marsden came up at the end of that paper to introduce himself. He had come from London. He had just finishing his residency. He had shown a medical student the phylogeny of the nigra, how it gets bigger and bigger, higher order of animals, but more and more pigment. But it looked to be a dead organ, he thought, and the pigment was just deposited there. And so he was amazed at our work, and we hit it off, and we went to the World's Fair to get the Expo. I remember riding rides. We rode the roller coaster together. David was very excited. I wanted to sit on the first seat, the roller coaster, and get all the thrill of going up and down. And we sat with him and enjoyed it also, but not as much as he did. And we hit it off ever since, and so we were friends ever since then, and we sort of worked on movement disorders together after that. But also there was Mel Yar and Roger Duvazan. They saw those movies. There were movies in those days, no videos, Kotch's presentation, showing how these people, disabled, couldn't hardly move, and after a high dose of D-L-Dopa, they were walking around. So that was no humbug. I remember when we got back to New York, Mel Yar told the group that we got to work on this. We're going to go right to L-Dopa. We're going to do a double-blind trial. We got funds from NIH, do a double-blind trial. In the meantime, Kotch was already working on L-Dopa, and Kotch published first, of course, and that was his 1969 paper. No longer were the hematological side effects seen. You needed half the dose to get the benefit. Published in New England Journal of Medicine also, and this is the title page of his paper. And Mel Yar published later that year, and published in the Archives of Neurology, the first double-blind trial in that year. And that set the stage. L-Dopa got approved by 1970 by the FDA. It was obviously revolutionary. I think the most exciting thing was happening in Parkinson's, and probably neurology at that time. And it couldn't be denied. That was so important, they had to get it approved and get it out there. This is the title page of Mel Yar's paper. Right away, a lot of people started working on it. Klawans here in Chicago published cases. McDonald Lee at Cornell in New York. By then, I was at the University of Pennsylvania when Bud Rowland went there, and I joined him. I teamed up with Gabe Schwartz, and we began treating patients with L-Dopa at UCLA, Markham, NYU, Lieberman, and Barbeau, and published his stuff in Montreal. And so everybody was agreeing this was an exciting development in the field of Parkinson's disease. So Kotches died before a Nobel Prize could be assigned. And I thought all three could have shared the Nobel Prize. They each had an important role to play. Without Kotches, we wouldn't have this. Yet without the other two, we wouldn't have it either, probably. Arvid Carlson and Oleg Hornikevich shared the Wolf Prize as the major Israel Science Prize in 1979. Carlson, I mentioned, got the Nobel Prize in 2000, shared it with Eric Kandel and Paul Greengard. Kachis immediately, the same year he published his L-DOPA paper, he got the Lasker Award that year. The only other, I think, neurologist to get the Lasker Award was, 2 years ago now, with Benabid and DeLong shared it for deep brain stimulation. Again, Parkinson's disease. You can see Parkinson's is very important in neurology. So what if Kachis had not tested the L-DOPA? I mean, it could have died on the vine before we really tested. I mean, low doses were ineffective, needed to be injected, difficult to prepare. Benefit was really grave doubt. People couldn't prove that it was useful, and we might have lost a superb treatment. And I even speculate that probably Carlson would not have won the Nobel Prize later if there wasn't a good treatment for dopamine precursor. So this is a really important milestone in the history of neurology, I think, in general, but also a lesson how things, you can use something for the wrong reasons but get the right results. Kachis did it for the wrong reason, got the right results, but he knew how to use it right. He was wise enough to use the small dose approach and avoiding side effects. And I thank you very much for having me here. I enjoyed giving this talk to all of you. And thank you again, Tao, for inviting me.